Would you be willing to give up everything you thought you knew about time? In short, there is no such thing as time. This is not just our opinion. It's also the conclusion of a new study. However, what does this crazy assumption mean? How come what we normally think of as time might just be a dream created by quantum physics? What are the implications of this radical idea? Einstein once said, "For us physicists, the difference between the past, the present, and the future is just an illusion, albeit a stubborn one. Subjective time, which is focused on the present, doesn't have any objective meaning." In fact, the more we learn about this subject, the more strange things become that we find so ordinary in our daily lives. The question of what time it is usually not even considered, since time is usually just a few numbers on the clock or a certain day on the calendar. By definition, however, we are talking about a physical quantity that describes the order of events in a single, unchangeable direction. This quantity has an impact on everything, since the universe moves both in space and time, from the Big Bang to the end. So, time moves in a straight line, but it still surprises us with new problems every day. As we said at the beginning, a new study has found that time is not a fundamental part of the world at all. Instead, it is just an illusion caused by quantum entanglement. But what does that mean? Does this mean there isn't a start and an end? That's too bad. It's not really that easy. To understand why time is still the subject of so many scientific debates, we should first look at the different ways that experts can approach the subject. That's one side of things. Einsteinian physics shows how the universe works on a large scale. Quantum mechanics, on the other hand, looks at things on a very small level and often seems to go against traditional physics. Let us think about Schrödinger's cat, which is at the heart of a thought experiment written in 1935 by the scientist with the same name. In this story, a cat and a poison pill are locked in a box, but no one knows when the poison will get out. So, the cat can be thought of as both dead and living at the same time. You would have to see it change its state to see it change between the two. What does a cat in a box have to do with quantum physics, though? Well, it's pretty easy to explain. Quantum mechanics also understands this kind of superposition, which means that different states can be stacked on top of each other. The equivalent system only takes on one of the superimposed states when a measurement or observation is made. Schrödinger's goal at the time was to show that classical and quantum mechanical physical concepts do not work together, since a cat cannot be both dead and alive at the same time. But superposition is also a part of the wonderful world of quantum coupling. Normal quantum theory says that particles don't really have a single state. Instead, you can give them relative chances of being in one state or another. It has already been said that this only changes during a test if the particle takes on one of these states based on these odds. But things get even stranger when two particles connect with each other, because that's when they can get tangled up. In other words, their separate probabilities are no longer separate from each other. They are now connected to each other and make up a complicated probability function that describes both particles equally. Let's look at an example to better understand this. In an experiment on entanglement, two electrons are made at the same time, and the intrinsic angular momentum, or spin, of each is recorded in two different devices. In the end, it turns out that each electron has the opposite spin. This is even more surprising because, according to the superposition, their state wasn't known at all before the test. In the end, the measurement was the only thing that made one particle choose one state and the other particle choose the other state at the same time, even though they were far apart. So, we should think of the two electrons as a coherent system. But quantum entanglement also goes against the idea of locality, which says that processes can only affect their near surroundings in space. With quantum entanglement, the particles that are entangled can be light years apart, but still can't be broken apart. In addition, the particles that are spread out in space share information instantly, that is, there is no time delay. Given this, it's not a surprise that Albert Einstein had trouble with the idea of spooky action at a distance. Really, the information would have to be sent faster than light for that to work. Quantum entanglement can be hard to understand at times, but it may now give scientists the chance to finally figure out what time is all about. Is time really just a dream? The study from the Italian National Research Council was published in the journal Physical Review A. The lead authors of the study say that time can fit with both the traditional laws of physics and the rules of quantum mechanics if it is a manifestation of entanglement. But first things first, in quantum physics, time is a fixed thing that always moves from the past to the present. Time, on the other hand, stays outside of quantum systems, which are strange and always changing. You can tell time by looking at changes in outside units, like the hands on a clock. But Einstein's general theory of relativity says that time and space are connected, and that time and space can be warped and stretched in the process. Scientists were stuck for a long time because of this difference between classical and quantum mechanical rules. But the study stated above now makes it seem like time may only be an illusion caused by quantum entanglement. Anyhow, what does that mean? In fact, quantum physics has dealt with the time problem before. A theory called the Page-Water mechanism was first put forward in 1983. It says that time only exists for an object when it is quantumly connected to another object that works as a clock. But for a system that isn't entangled, there is no time at all. It sees the world as frozen and not changing. Researchers found that the Schrödinger equation, which describes how quantum objects behave, could be used to describe their system when they applied it to two hypothetical quantum states, a buzzing oscillator and a group of tiny magnets working as a clock. But time wasn't used directly. The states of the tiny magnets acted as the clock. In the next step, the experts did their math twice more, this time assuming that the magnetic clock and then the oscillator were made up of macroscopic, or large, things. Their equations were simplified to those used in classical physics. This shows that the flow of time happens because of entanglement, even for very big objects. In this case, the experts stressed that they should start with quantum physics and figure out how to move on to classical physics, not the other way around. But some experts have been a little more careful in what they've said. It makes sense theoretically to think of universal time as a connection between quantum fields and quantum states of 3D space. But no one is sure if this picture will lead to something new or useful, like changes to quantum mechanics and the general theory of relativity. When the galaxy sent out light, it warped it, making the Einstein ring around SDSS J 1226 plus 2149. Light is stretched into the shape of a ring by the mass of a galaxy cluster in the way it has twisted and stretched it. Not only is the stretching an interesting physical effect in this case, it also makes things behind it much bigger. In this way, an Einstein ring works like a gravity lens. Researchers can see things that are very far away and almost unnoticeable to the naked eye because of these two effects. The first Einstein ring to be seen was in the galaxy cluster AEL 370, before these effects were known. This cluster even has one of the most beautiful examples of a full Einstein ring that has ever been seen. Astronomers could look at the faraway galaxy in great detail and learn about its structure and the rate at which stars are being born in it because of this effect. The Einstein ring around AEL 370 is not only a fantastic feature, but it is also a great example of how the general theory of relativity works in real life and continues to lead to new finds in astronomy. Astronomers have been able to see many more things in the world thanks to gravitational lensing. One of these things is the galaxy GN-Z11, which is one of the oldest and farthest away galaxies ever found. It will be written in the history books of science. It is about 13.4 billion light-years away and was formed not long after the Big Bang, about 400 million years ago. Astronomers were able to learn a lot about this galaxy's structure and makeup thanks to the lens effect, which made the light from it brighter. Gravitational lensing allowed even the Hubble Space Telescope to make this finding, even though scientists thought it was past its useful life. Gravitational lensing was also used to find Max J1149 plus 2223 Lens Star 1, which is the farthest single star ever seen. The star is in a galaxy that is about 9 billion light-years away. Because of the gravitational lensing effect of a group of galaxies between Earth and the star, the light from this star would be too weak to be seen at all. The gravitational lens made the light about 1,000 times brighter, which let scientists study a single star from so far away in great detail for the first time. Scientists really enjoy finding single stars from very long ago. We can now break with the help of the James Webb Space Telescope. Light signals from stars like Max J1149 plus 2223 can be broken down into their constituent parts. This lets scientists quickly get accurate studies of the gases and elements that made up the stars in the early universe.